Welcome back to the deep dive. Today, we're doing something a little different. We are shifting gears.
Yeah,
We're not just observers today. We are, stepping into a very specific role.
That's right.
I want you to imagine for a moment that we are sitting in a boardroom. Maybe it's in Stuttgart, maybe Detroit, could even be a high-rise in Shanghai. And we are here acting as senior technical strategy consultants. We've been hired by a top-tier global automotive engineering firm.
Exactly. And the client sitting across the table, it's not the marketing team, it's not sales.
Yeah.
We are briefing the senior automotive engineers, the technical directors, the CTOs. I mean, the people who actually have to design and build the machine.
The ones with the really hard problems to solve. So because of that, the tone of this deep dive is going to be a bit different.
It has to be.
It's going to be high level, definitely strategic, but uncompromisingly technical. We're not dumbing anything down today.
Yeah. Nope. We're taking a whole stack of reports. Everything from simulation giants like VI Grade to software infrastructure leaders like Perforce and Electrobit, plus a ton of market analysis. And we're synthesizing it all.
We're boiling it down into a definitive technical strategy report.
A single source of truth for them. And we're going to use a classic McKinsey-style approach here.
Okay.
We're going top-down, start with the big picture, and drill in. And we're aiming for MEC.
MEC.
Mutually exclusive, collectively exhaustive. Basically cover all the bases without repeating ourselves. The goal is to lay out the entire landscape for the global human-machine interface, or HMI, for this really critical period of 2024 to 2026.
A very tight, critical window. Okay, so let's start where any good report starts.
Yeah.
The headline, the executive summary, if you will.
Let's do it.
For the past decade, let's be honest, the strategy has been pretty simple. I'd call it screenification.
That's a good word for it.
Right. Just make the screen bigger.
Yeah.
If the competitor comes out with a 12-inch screen, we need a 15. If they have a 15-inch, we need to go pillar to pillar.
It was an arms race of screen real estate. And that era is officially dead.
Over.
The data is crystal clear on this. The whole smartphone on wheels analogy, which drove everything for years, is now obsolete.
So it's replacing it.
We are entering a new paradigm. The sources we've analyzed are calling it the era of cognitive interaction and phygital fusion.
Physical plus digital.
Exactly.
I have to admit, I love that word, even if it does sound a little bit like a marketing buzzword.
Yeah.
But there's a very hard, very real catalyst behind this shift, right? It's not just a trend.
Oh, absolutely not. This is not an aesthetic choice. It is a collision of three massive, unstoppable forces.
Okay, let's hear them.
First, you've got a regulatory shockwave coming in 2026. Euro, NCIPP. It effectively bans the all-touch interface for safety-critical functions. It's a hard stop.
Wow. Okay, that's number one.
Second, the rise of generative AI. And not just in the cloud, like ChatGPT. We're talking about AI moving to the edge, into the car itself.
On device.
On device. And third, you have the fundamental collapse of distributed computing architectures into what we're calling one-chip systems.
Three massive forces colliding at once. That is the perfect setup. So let's unpack this piece by piece. Let's start with section 1, the executive summary and market landscape, the why behind this whole strategy.
Right.
You mentioned the smartphone on wheels model is dead. What's the new mental model for the engineers to latch onto?
The new mental model is a spatial computing environment.
Spatial computing, so like Apple's Vision Pro, but for your car.
In a way, yes. It's no longer about a flat grid of apps you poke at. It's about depth, it's about perception, and most importantly, it's about trust between the driver and the machine.
Yeah.
There's a fantastic quote from BMW's CEO, Oliver Zips, that's referenced throughout our sources, and it really anchors this entire shift.
What do you say?
He said, "Digital leadership isn't about who has the largest screen. The only thing that matters is the user experience."
Which sounds great in a press release or an annual report. But from a technical strategy perspective, that means a fundamental shift in where the R&D money goes.
Precisely. You have to follow the money. If you look at the market valuation, the KGR, the compound annual growth rate, it's sitting somewhere between 11 and 14%, depending on which analyst report you trust.
Which is healthy growth.
Very healthy. But the value within that growth is shifting dramatically. It's moving away from the traditional commodity suppliers.
Yeah.
The companies that just stamp out big LCD panels.
Their lunch is being eaten.
Their lunch is being eaten by the software stack and the AI integration. The hardware, the screen itself is becoming a commodity. The software, the experience, that's the differentiator now.
That's where the profit margins are. Now, within this market landscape, we have to address the elephant in the room, The reports call it the two-speed world.
We absolutely do. You cannot create a global HMI strategy without understanding this divergence. It's massive.
A bifurcation between East and West.
A total bifurcation. On one side, you have China. They are the ecosystem exporters.
What does that mean in practice?
It means they are operating on a 24-month development cycle, from concept to production.
24 months.
Ah.
That's basically a smartphone development cycle. It's insane for a car.
It's blistering speed,
Yeah.
and it's driven by a completely different consumer psychology. In China, the consumers are, for all intents and purposes, beta testers.
They're willing to accept bugs.
They are tolerant of flaws and glitches in exchange for getting the newest, coolest features first. They expect their car to be deeply, seamlessly integrated with the Beidou ecosystem.
Beidou being Baidu, Alibaba, Tencent.
Exactly. Their entire digital life. If your car's HMI doesn't feel like a native extension of WeChat or Alipay, it's considered obsolete the day it comes out.
Okay, so that's one speed. What's the other? Europe and North America.
We're calling them the sovereignty defenders.
I like that.
And they're stuck in 36 to 48-month development cycles, sometimes even longer.
So double the time. Why? What's holding them back?
Two big things. First, a rigorous, almost religious adherence to functional safety standards, specifically ISO 26262.
The Bible of automotive safety.
It is. And second, privacy regulations like GDPR. They are, in essence, building digital bank vaults on wheels. The Chinese OEMs, by contrast, are building high-end gaming PCs. Very different philosophies.
And the strategic implication for our client, for you, the listener, is what?
The strategic implication is that Western OEMs are at serious risk of architectural rigidity.
Meaning they're locked in.
They're locked in. By the time they finish the painstaking process of validating a system against ISO 26262, the digital ceiling, what's even possible in terms of features, has already been raised 2 or 3 times by their Chinese competitors.
So our mission, our core task in this deep dive is to figure out how to balance those two speeds. How do you move faster without breaking those critical safety protocols?
That is the multi-billion-dollar question.
All right, let's move to section 2. This feels like the first big piece of that puzzle, the digital renaissance. You frame this as a regulatory strategy.
It is. It's not optional.
You mentioned the Euro NCAP 2026 rules. You called it a shockwave. That sounds dramatic.
It is a massive shockwave. I don't think all the design studios have fully internalized what's coming. Effective January 1st, 2026, the new Euro NCAP safety protocol kicks in.
And the big rule is?
To get a coveted 5-star safety rating, which is everything in the European market, specific eyes-off-road functions must have dedicated single-action physical controls.
So the party is over for the everything on the touchscreen philosophy.
The party is over and the cleanup has begun.
Let's get specific. Let's list them. What are the functions that absolutely must come back out of the submenus and into the physical world?
It's what the report calls the must-have list. It's short, but it's non-negotiable.
Okay.
Number 1, turn indicators.
Makes sense.
Number 2, hazard warning lights.
Of course.
Number 3, windscreen wipers. All functions, speed, intermittency.
Oh, that's a big one. I've been in cars where that's buried in a menu. It's terrifying in a sudden downpour.
Exactly. Number 4, the horn. And number 5, the e-call or SOS function.
So no more desperately swiping through 3 submenus on a greasy touchscreen just to turn on your wipers while you're hydroplaning on the Autobahn.
That exact nightmare scenario is what's driving this regulation. But here's the engineering implication, and this is where it gets really technical for our audience.
This is what they need to know.
This isn't just about telling the design team to glue a button back onto the dashboard. This creates a fundamental redundancy problem at the architectural level.
How so?
In the screenification era, a lot of those so-called buttons were just soft keys rendered on an Android or Linux screen. The signal path went from your finger to the touch sensor, through the main operating system, and then out to the component.
Okay, I see where this is going. But if Android crashes...
If the infotainment OS has a kernel panic because you tried to run a buggy app, you lose your turn signals. You lose your wipers.
That's completely unacceptable under the new protocol.
It's an instant fail. So we now have a critical signal routing challenge. The signals from these new physical controls must completely bypass the main infotainment OS.
A dedicated, hardwired path.
Exactly. They need to be routed directly to the body control module, the BCM or the main gateway via low latency, high reliability paths like CAN or LAN bus.
But the designers, The
Yes.
interior design teams are going to scream. They've spent a solid decade cleaning up the cockpit, removing every last bit of physical clutter. Now we're marching in and telling them to put buttons back.
And that is the central design challenge of the next 24 months. How do you reintroduce physical buddies without completely ruining the clean, minimalist aesthetic that consumers now expect?
It's a paradox.
It is, but the report points to a very specific and I think very elegant technological solution.
Which is?
Piezoelectric haptics.
Piezohaptics. Okay,
Okay.
break that down for us. This is not the same as the cheap vibration motor in your phone, right?
Not even in the same universe. A standard vibration motor is just an unbalanced inertial mass spinning around. It's sloppy, it's vague,
You just feel a general buzz.
a general buzz. Piezoelectric actuators are solid-state ceramic components that deform with incredible speed and precision when you apply a voltage.
So what does that let you do?
It lets you simulate incredibly detailed textures and feedback on a perfectly flat surface, like a piece of glass or wood. They can make a spot on a glass screen feel like a mechanical click when you press it, or they can make it feel rough like sandpaper or like you're dragging your finger over a grill.
Whoa. So you could have a single seamless piece of glass for the center console that looks completely clean and digital.
Right.
But when you run your finger down it, you can actually feel the distinct raised edge of the virtual button for the hazard lights.
Precisely. You get the best of both worlds. The goal here is what the report calls intuitive redundancy.
Intuitive redundancy.
You allow for blind operation eyes-free interaction through muscle memory and that crucial tactile feedback. But you maintain that sleek, seamless black panel look when the car is off. It's the perfect technical compromise between the digital aesthetic the designers want and the physical safety requirement the regulators demand.
That is a fascinating and really elegant pivot. It's not going backward, it's going forward in a different way.
It's a phygital solution.
Yeah. Let's go deeper into the machine. Section 3, compute architecture strategy. This is the foundation.
Yeah.
You mentioned at the top that we're seeing a one-chip revolution.
Yes. This is, without a doubt, the biggest architectural shift in automotive electronics in 30 years. We are witnessing the end of the distributed architecture.
Explain what that means. Historically, what did the layout look like?
Historically, and even in most cars on the road today, you had a whole collection of separate boxes, separate ECUs. You had one box for the infotainment system, we call that the cockpit domain, and you had a completely separate, powerful box for the automated driving functions, the ADS domain.
Two different computers, often from two different suppliers, running two different software stacks.
Exactly, a huge integration headache. Now we are merging them. Both of those domains are collapsing onto a single, incredibly powerful system on chip or so.
And this has created a bit of a silicon arms race, right? A battle of the titans to own that single spot in the dashboard. Who are the main combatants?
It's a true heavyweight bout. In the red corner, you have the supercomputer approach.
Yeah.
This is NVIDIA with their Drive Thor platform.
NVIDIA, the AI and gaming giant.
The very same. The Thor chip is an absolute monster. It's aiming for around 2,000 TOPS.
2000 TOPS. Break that down. What is a 2P?
A type E is a trillion operations per second. It's a measure of raw integer math performance, which is crucial for running neural networks. So we're talking about 2 quadrillion operations per second.
That's an astronomical number.
It is. Thor uses their latest Blackwell GPU architecture. This chip is squarely aimed at OEMs who want to dominate level 3 and level 4 autonomy. It's not an exaggeration to say it's like putting a server rack in the dashboard.
Okay, so that's NVIDIA's brute force approach.
Yeah.
Who's in the blue corner?
In the blue corner, you have Qualcomm. They're coming at this with their Snapdragon Cockpit Elite platform, and theirs is the ecosystem approach.
What's their TOPS number?
It's around 362 PS, so significantly less raw brute force than Thor.
But still very powerful.
Oh, absolutely. But Qualcomm's focus is different. They're emphasizing power efficiency, gaming-grade graphics performance, and most importantly, deep native Android compatibility. They're leveraging their complete dominance in the high-end mobile phone market.
Okay, but this brings us to a terrifying question.
Yeah.
If we are putting everything on one single piece of silicon, the speedometer, the warning lights, the ADS system, and the kids' video games in the back, doesn't that create a colossal risk?
It does.
I mean, if the game crashes, does the speedometer just disappear at 100 miles per hour?
That is the freedom from interference, or FFI challenge. And it is the single biggest technical headache and validation nightmare in this entire consolidated architecture. How do you run a safety-critical real-time operating system like QNX right next to a bloated consumer-grade OS like Android Automotive on the same cores without one ever being able to kill the other.
It seems impossible. What's the solution?
The solution is virtualization. Very robust virtualization. Specifically, we use what are called Type 1 hypervisors.
A hypervisor. Like in data centers.
Exactly like in data centers, but certified for automotive safety. Technologies like the QNX hypervisor or the open source project ACRN that Intel started, they act as a traffic cop at the lowest level of the hardware. They create strict, ironclad, non-negotiable walls between the different software partitions.
So Android literally can't see the memory or the CPU cycles being used by the instrument cluster?
It's completely invisible to it. But software alone isn't enough. The hardware has to help too, and that's where we're seeing the emergence of a concept called the Functional Safety Island, or FSI.
A safety island. Tell me more.
Think of it as a tiny, self-sufficient bunker built right into the silicon of the main chip.
A bunker.
It often has its own independent power supply regulator, its own separate clock source, and maybe even a small, dedicated CPU core. The idea is that even if the main high-performance part of the chip completely melts down, a catastrophic failure due to a gaming glitch or a memory leak in a third-party app,
The island survives.
the FSI just keeps ticking along completely unaffected. It has one job: keep the speedometer drawing, keep the warning lights flashing, keep the basic survival functions of the car alive. It is the absolute last line of defense.
That is incredibly clever and also deeply reassuring. Okay, so we've established the hardware foundation. It's solid, it's virtualized, it's redundant. Now let's talk about what the user actually sees and interacts with. Section 4, Visual and AI strategy. The experience itself.
Right. Visually, the biggest story is the game engine revolution.
This still blows my mind. We're using video game technology to design car interfaces.
We are, and not just any engines. We're talking about the absolute top-tier Unreal Engine 5 and Unity. They are rapidly becoming the de facto standard for modern HMI development.
Why now? What changed?
The hardware just got powerful enough. Those Sarshes we just talked about have GPUs that can finally handle it. The result is that the graphics in your car's navigation system can now rival a PlayStation 5 with real-time lighting, reflections, and physics.
But to display all that beautiful imagery, you need the right screen hardware. We hear a lot about OLEDs, like in high-end TVs. Are they the answer for cars?
OLEDs are tricky. They produce beautiful, perfect blacks and vibrant colors, but they're very risky for automotive applications.
Wow.
The problem is burn-in, or image retention. A car interface has many static elements: the speed limit sign icon, the fuel gauge, the gear selector display that sit in the exact same pixels for hours and hours on end.
And OLEDs are organic, so those pixels degrade over time if they're always on.
Exactly. You end up with a ghost image permanently burned into the screen. The current sweet spot that's clearly identified in the report is Mini LED.
Mini LED.
It's still an LCD panel, so it's robust and doesn't suffer from burn-in, but it uses thousands of tiny LEDs in its backlight, creating hundreds or thousands of local dimming zones. This lets you get really close to OLED-level contrast without the reliability risk.
And what's the future beyond Mini LED? What's the next target?
The holy grail is micro LED. This is the ultimate display technology. Insanely high brightness for sunlight legibility. It can be made transparent, and it has no burn-in because it's inorganic.
So what's the catch?
The manufacturing cost. Specifically, a process called mass transfer, which involves picking and placing millions of microscopic LEDs onto the display backplane with perfect accuracy. It's still way too expensive for mass automotive adoption. It's the target for maybe 2028, perhaps later.
Okay, what about displays that aren't on the dashboard? What about the head-up display, the AR HUD?
The augmented reality head-up display is a major battleground, and it's really a battle of fundamental physics.
Oh, battle of physics.
Yes. You have a few competing technologies. There's LSOS liquid crystal on silicon, which gives you incredible pixel density and resolution. Then you have laser beam scanning LBS, which uses mirrors to draw the image with lasers, giving you basically infinite contrast and vibrant colors.
And there's a third.
And then you have waveguide technology, which is what things like the HoloLens use. This is the ultimate goal because it uses optics to massively shrink the size of the projector unit.
Which is a huge problem, right? The current AR HUD units are massive boxes.
They're the size of a shoebox, and they take up all the space in the dashboard where you want to put HVAC components. Waveguides are the key to making AR HUDs mainstream.
Right. Now, let's pivot from the visuals to the brain of the experience. AI. Everyone wants to put ChatGPT in their car, but the strategy report says that cloud AI is a trap.
It is a huge trap, and the killer is one single metric: latency.
The delay.
Delay. If you're in your car and you say, hey car, turn on the front defroster, and that voice command has to be sent to a server in another state, processed, and the response sent back, you're looking at a 3 to 5 second delay.
Which, in a driving scenario, feels like an absolute eternity.
It completely breaks the immersion and the trust. It's frustrating. So the key performance indicator, the KPI that every HMI team needs to be obsessed with, is TTFT.
TTFT.
Time to first token. It's a measure of how quickly the AI starts generating its response. For a natural conversational interaction, the TTFT must be under 1 second, preferably under 500 milliseconds.
If it's longer than that.
If it's longer, the user stops treating it like a conversation and starts treating it like a slow, frustrating command line.
So how do we get that speed? How do we achieve sub-second TTFT?
Edge AI. The processing has to happen on device. We cannot rely on the cloud.
But these AI models are huge.
They are, so we have to quantize them. That's the key technical term. We shrink them down, typically from 32-bit floating point precision to 8-bit integer, or INT8.
You make them less precise, but much smaller and faster.
Exactly. Small enough to run efficiently on the car's own dedicated neural processing unit, the MPU. We are not sending your data to a remote data center. The car is the data center.
But there's another risk with these on-device AIs, the risk of hallucinations. You can't have the AI just making things up about how the car works.
That's the nightmare scenario. The driver asks, hey, why is that red light with the exclamation point on? And the AI says, oh, that means your pizza is ready.
That's a disaster. So how do you prevent that?
The solution is a technique called RAG retrieval augmented generation.
Okay, right.
Before the AI is allowed to generate an answer, we force it to first retrieve relevant information from a trusted local source.
Like what?
Like the car's own digital owner's manual or real-time data from the vehicle's sensors. We essentially force the AI to check the manual before it opens its mouth. It grounds the AI in the specific reality of that vehicle.
So it's not just generate an answer. It's check the manual, then generate an answer based on what you found.
That's smart. It's the only way to make these systems safe and trustworthy.
Okay, Section 5. This is where it gets real for the engineering teams listening. We have the hardware strategy, we have the AI strategy. How do we actually build this stuff? Software development and asset governance. The workflow.
This is where the rubber truly meets the road. And the first giant problem we're facing is something the reports call the digital content mountain.
A mountain of content.
Think about it. When you bring in game engines like Unreal, you're not just writing lines of text-based code anymore. You are suddenly dealing with thousands of massive multi-gigabyte 3D binary files textures, complex meshes, lighting models, animations.
And the traditional tools that software engineers use, like Git, really struggle with files that big, don't they?
Git absolutely chokes on large binaries. It's designed to track changes in lines of text, not a 2-gigabyte texture file. It becomes unusably slow.
So what's the strategic solution for managing this mountain?
The solution recommended across the board is a hybrid approach. For source code, you stick with Git. But for all the large binary assets, you use a system like Perforce, which is the standard in the video game industry, combined with a dedicated digital asset management system, a DAM.
The DAM.
The goal is to create a single source of truth, a unified system where the 3D artists working in Maya and the C++ coders working in Visual Studio are all pulling from and submitting to the same repository. If the artist updates the 3D model of the car's avatar, the coder needs to see that update instantly without breaking the entire build.
And what about that other classic bottleneck? Bridging the gap between the UI designer working in a tool like Figma and the developer who has to implement that design in code.
That has been a source of pain for decades. But there's a mature solution now called design tokens.
Design code.
It's a brilliant abstraction layer. Instead of a designer just picking a color, they define a token. They create a token called, say, brand primary blue. Then, instead of a developer hand-coding that specific hex value in 10 different places in the code, the system automatically exports the brand primary blue token as native code, as JSON, as XML for Android, as CSS for a web-based component.
So if the marketing department decides to change brand primary blue next week,
you update the value of the token once, in one place, and it automatically propagates everywhere across the entire software stack. No developer has to go in and refactor hundreds of lines of code.
That's incredibly powerful.
It is. And this enables something really cool called RRO Runtime Resource Overlay. This is a native Android technology that's a huge enabler for personalization.
What does it let you do?
It allows for dynamic theming. Because the colors and fonts are defined by these tokens, you can swap out the entire theme of the car's interface at runtime. You can switch the UI from a bright sport mode red theme to a calming eco mode green theme instantly, without needing an over-the-air update and without recompiling the app.
That's the kind of customization that people coming from the smartphone world just expect now.
Exactly. But we have to layer safety on top of all of this speed and flexibility. ISO 26262 is always watching.
It never sleeps.
It never sleeps. For any safety-related screen, you need what's called a chain of evidence. Every single pixel on that screen, the numbers on the speedometer, the battery warning icon, must be traceable all the way back to a formal requirement, a design document, and a test result that proves it works.
So you need processes in place.
You need controlled check-ins and safety baselines within your DAM and your Perforce system. You cannot, under any circumstances, allow an unverified texture file that an artist just created to make it into a production build that controls the instrument cluster. The entire asset pipeline has to be compliant.
A huge challenge.
Yeah.
Okay, moving on to the next link in the chain, Section 6. Validation strategy. We've designed it, we've coded it. How in the world do we test something this complex? The report advocates for a zero prototypes approach.
Yeah, and that sounds radical, but it's becoming a necessity.
Why? What's wrong with building physical prototypes?
Two things. First, they're just too slow and too expensive in this new 24-month world. But there's a much deeper, more fundamental problem, which the report calls the curse of rarity.
The curse of rarity. That sounds ominous.
It is. Think about a critical level 3 autonomy scenario. The car is driving itself on the highway, but suddenly it encounters a freak blizzard, and it needs to hand control back to the human driver.
That handover moment is the most dangerous part.
It's incredibly dangerous. How do you test the HMI for that? How do you ensure your warnings are clear and effective? You can't just take a multi-million-dollar prototype out on a public road and hope a blizzard happens. These critical edge cases are, by their nature, rare.
So you can't test them in the real world. You have to simulate them.
You must. And we're not talking about a developer just running some software on their desk. We're talking about full immersive simulation. We're talking about compact HMI simulators.
Describe one of those. What does it look like?
It's a physical rig. It has a real steering wheel with force feedback, real pedals, a proper car seat. And instead of a normal monitor, it's connected to a massive 98-inch curved screen, or increasingly, a high-end VR headset.
What's the software running the world inside that simulation?
The prime example given is a platform like VI World Sim. It's what we call a visual digital twin of the world. It doesn't just generate realistic traffic, weather, and pedestrians.
What else does it do?
Critically, it simulates the vehicle's sensors. It generates fake but physically accurate data for the LiDAR, the radar, and the cameras. So the car's actual ADAS computer thinks it's seeing a real car cut it off in the rain, and the HMI has to react accordingly. You can test those rare scenarios 1,000 times a day.
There's a fascinating case study mentioned in the report. Lamborghini?
Yes, Lamborghini. And what's so interesting is they aren't just using these simulators to test for bugs, they're using them to test for emotion. Yeah. They use simulation to tune the emotional feel of the digital cockpit. Are the animations satisfying? Does the sound design make the car feel powerful? They are iterating on the core user experience at a speed that physical modeling could never, ever match, long before the tooling for the real dashboard even exists.
And VR plays a role in the physical design, too.
Mixed reality specifically, using very high-end headsets like the ones from Varjo. An engineer can sit in a simple wooden buck, just a basic frame of the car, put on the headset, and see the entire finished interior rendered in photorealistic detail around them.
They can check ergonomics.
Exactly. Can I comfortably reach that part of the touchscreen? Is the A-pillar creating a dangerous blind spot? You can answer these crucial human factors questions months or even years before you have to cut the first piece of steel.
Incredible.
I know.
And there was one more highly technical nugget in this validation section. Ground truth labeling.
Yes, this is a huge accelerator for the AI teams. To train the perception algorithms for the ADS, you need vast amounts of labeled data. You need pictures where someone has drawn a box and said, this is a pedestrian, this is a stop sign.
Then doing that manually is incredibly slow and expensive.
Excruciatingly slow. But in the simulator, the computer knows it just generated a pedestrian at a specific set of coordinates. So it can automatically label its own training data. It can generate ground truth for free. This speeds up the machine learning training pipeline by orders of magnitude.
It's a self-feeding loop. That's amazing. Okay, we have covered a massive amount of ground. We've done the market landscape, the regulatory shock, the silicon, the experience, the workflow, and the validation. Now, as consultants, it's time to deliver the final verdict. Section 7, the roadmap, the actionable recommendations.
This is it. We've distilled everything we've discussed down to 4 clear, non-negotiable strategic directives for the 2024 to 2026 period.
All right, let's hear them. Directive number 1.
Implement a zero prototypes philosophy. You must move at least 80% of your human factors and UX evaluation into virtual simulators before the A-sample hardware phase. If you are waiting for a physical car to test your user experience, you have already lost the race.
Get it right in the virtual world first.
Okay.
Directive number 2.
Adopt design tokens universally. Stop hard-coding styles like colors and fonts. You must enable dynamic theming via runtime resource overlay. This is the only scalable way to keep up with the customization demands of the modern market without drowning your software team in technical debt.
Decouple design from logic. I like it. Directive number 3.
Build the single source of truth for your assets. Do not try to manage massive 3D binary assets in Git. It will fail. You must deploy a professional digital asset management system, a DAM, and it has to be compliant with ISO 2626262 processes. Bridge the gap between the creative design studio and the safety-critical engineering lab.
One pipeline for everyone. Makes sense. And finally, directive number 4.
Intuitive redundancy. Start preparing for Euro NCAP 2026 today, not in late 2025. You must begin the process of reintegrating physical controls, or preferably high-fidelity piezo-haptics, for those 5 safety-critical functions. Do not let the clean design dogma from the last decade compromise your 5-star safety rating.
4 powerful, clear directives. So let's wrap this entire deep dive up with a final synthesis. If you had to boil this entire strategy down to one word, what is the winning theme here?
The winning strategy is balance. That's the single word.
Balance.
It's about balancing the cool factor of those beautiful game engine graphics with the non-negotiable survival factor of functional safety. It's about balancing the incredible breakneck speed of Chinese software iteration with the methodical rigor of Western safety standards. You cannot just pick one side of that equation. The winning OEMs will be the ones who become masters of the hybrid approach.
And as we always do, a final provocative closing thought for our listeners, our CTOs, our technical directors, our senior engineers out there. Something to chew on.
We talk a lot about the user experience, UX, but I think we need to go deeper than that now. If the car is truly becoming a third living space, and the interface is becoming cognitive, it's aware of you, it talks to you, it anticipates your needs,
Right.
then are we still designing a vehicle? Or are we now, in fact, designing a relationship?
A relationship between human and machine.
Exactly. And I believe the engineers and the strategists who understand that fundamental distinction, that they are building a companion, a trusted partner, not just a tool to get from A to B, they are the ones who will win the next decade.
That is the perfect place to leave it. We hope this technical strategy report serves you well in your next board meeting. Go build the future of mobility.
Stay safe and stay innovative.
We'll see you in the next deep dive.